what is an adjoint of a linear operator on an inner product space. And then we also saw some results related to linear functional on an inner product space. So let me recall what we did in the last class. So in the last lecture, we saw that if we have a if we have an inner product space V over some field F, and if we fix a vector in V, let's say U, then depending on this vector U, we can define a linear functional on V that we can denote by F under F subscript U V to F. And how it is defined, you take any vector in V and send it to the inner product of V with U for all V. Now this you can check that this is a linear functional on V, and this we can do for every vector in the inner product space. In fact, we saw that then we asked this question whether the converse is also true. That means if we are given a linear functional F, then can we find a vector in V such that this F has this form? Now the answer of this question is not true, or we cannot do it if V is an infinite dimensional inner product space. But if V is a finite dimension inner product space, then we can always do it. So basically, for finite dimension inner product space, we can say that if V is an inner product, V is a V is a finite dimensional inner product space, then we can say that if F is any linear functional on V, then there exists a the uniqueness also we saw, there exists a unique vector, let us denote it by UF in V, such that this F has this form, F of V is equal to inner product of V with UF. This is true for all V in the inner product space V. This is true for finite dimension inner product space. And then we define adjoint of a linear operator. So what is an adjoint of a linear operator on an inner product space? So if we have an inner product space again V, and if T is a linear operator on V, then adjoint of adjoint of T is a linear operator S on V that satisfy this property that says that inner product of T of U with V is equal to inner product of U with S of V. And this is true for all vectors UV in V. If this is true, then we call S as an adjoint of T. But we saw that we did not talk about the existence of the adjoint of a linear operator, but we saw that if adjoint exists, then it is always unique. So uniqueness is true, and therefore we can denote this adjoint by this notation T star. So the existence is not clear at this point, but if it exists, then it is always unique. This is also we saw in the last class. Then I mentioned that the existence in an infinite dimension inner product space is not true and need not be true. So that means if we have an infinite dimension inner product space, and if we have a linear operator on that inner product space, that operator need not have an adjoint on V. This is infinite dimension inner product space, and the one can find an example also, and you will see that the way we will prove for the finite dimension case, it's sort of clear that because of this result uh, here, this is not true for infinite dimension case, and therefore it's not possible to do it for any infinite dimension space. You'll need some other conditions only. Okay, so let us prove this result for finite dimension. That means if V is a um, finite dimension inner product space and T is a linear operator on this, then it will always have its adjoint. Okay, so let us start today's lecture by proving that. All right, so let me write the result first. So let V be a finite dimension inner product space, and suppose that T is a linear operator on this V, then then T, or you can say, or yeah, T has an adjoint, then T has an adjoint on V. What does it mean? That means there exists a unique operator T star on V such that this relation is true. This relation is true for all vectors u and v in V. Okay, so let us prove this. So what we have to do here in the proof, we have to find a linear operator on V, it's a T star, such that this relation is true. This we have to keep in mind while defining this operator T star. So we want a linear operator on V such that this relation is true. Okay, so let what I will do here. So let us see this first. So if I take any vector, so we want to define T star, right? So if I take any vector, let's say u in V, and based on this vector u, I'll define this functional f on V. How would I define? I'll take any vector in V and send it to T of V u for all V in V. Okay. So for any fixed vector u here, I will define this linear functional f this way. Okay. Now you can verify that this is a linear function. This is linear because of the fact that T is linear. So you can verify that this f, whatever I have defined here, this is a linear functional of V. So for every vector u, I can define a functional on V this way. Okay. Now, since this is a linear functional on V, and we know that since it's a linear functional from the from the observation in the last lecture, we know that there exists a unique. So this implies that there exists a unique, let's say UF in V. This is just a notation depending on this F. There exists a unique vector. Let's denote it by UF, such that f of V is equal to V, inner product of V with UF, right? But then what is left hand side? So left hand side here is T of V u. Now you can see here, can you get some idea? So this is true for every vector, for any vector u. So if I start with a vector u, I can define f in this form. But then I know that since this is a linear functional, so for this linear functional and V is a finite dimension inner product space, there exists a unique UF such that f can be written in this way, but f is actually defined this way. So this is so far this is what we have, and this is true. Now you can see that this is true. If you do it, you can do it for every vector u. Okay, so this is true, right? So now can you get some idea how to define this T star? So see here what I want. So let us see what we want. So we want to define a map T star from V to V, right? Such that it is linear and it satisfies this relation. Now, can you get some idea by looking at this here? How should I define this V so that this relation is satisfied? Can you give me some idea? Is there a way to relate vector here to here from this above whatever we did from this? Can you give some idea how to define this? Or if I take a vector here, then where should I send it to? Or to which vector I should assign to this? So here you see, I started with any vector u, and for this vector u, I have found somehow this vector uf, and this satisfies this relation. So now if I see here, if I assign u to uf, so that means I send u to uf, then this is a well-defined map because for every u, this is a unique uf because you can define f, but for this f, there is a unique uf, so you can send this u to uf in this way. And then if this is true, so what I'm saying is that now if we define, so if I define now, let's say T star, just a notation from V to V this way, that T star sends U to UF. Okay, you define this by this. Now it's clearly, so we need to check that this is, if we want to say that this is an adjoint, then we need to check that this is a linear operator on V, and it satisfies this relation here. Now, first see that this relation is immediate because of the way we have defined this T star, because how it is true, this is very straightforward. If I call this, let's say star, this expression, then from star you can see that clearly T of V U is equal to V UF, but UF is just T star U. And this is true now for all U and V in. So this relation is satisfied. So we are done if we just show that T star is a linear operator, right? So clearly this is true the way we have defined this. So we just need to show, in order to say that this T star is an adjoint of T, we just need to check whether T star is a linear operator or not. That means a linear transformation from V to V. Now to check the linearity, we just use the definition. So let us see whether this is true or not. So so please keep yourself muted. So let alpha belongs to, alpha is any scalar, and u and v are two vectors. Please, please keep yourself muted. Please keep yourself muted if you don't have anything to ask. So I'm muting you all so that there's no disturbance. Let me just check whether I can do that or not. So Nishu, can you mute yourself? Yes, thank you. Okay, so we just need to check whether this T star, the map we have defined, it's linear or not. So I'll just use the This is the property that this T star satisfy this thing. Okay, so let's see how to prove this. So so if I take this alpha and is scalar and u and v are two vectors, then you can check that for any vector w. So for any w in v, if you look at this one, so what I'm trying to do basically, I'm trying to show that this T star is linear by showing that this is equal to alpha T star u plus T star v for all w. So this is what we are trying to show. So we will try to show this. So if this is true, this relation is true for all w, then in particular I can take w as this vector itself, and therefore we'll get an equality here, right? So I'm trying to show that for any vector w, and if I fix this alpha and uv in v, then this is equal to this. This is what I'm trying to do here. So let us see why this is true. So from here, so can you tell me what I can do from here? What would be the next step?
TW.
So you're saying that use this property or what? Or
Yes, sir.
you mean this one? This one? Okay.
Yes,
So I
sir.
can write. Okay, I can write this as TW alpha u plus v. Then what?
Then then alpha. So
So we can open this
alpha
inner
conjugate.
product, right?
Yeah.
So we can write this as TW alpha u plus TW v. Okay, then from here I can write this as alpha bar TW because of the inner product u plus TW v. But then this is equal to alpha bar. What is this equal to? This is equal to W T star u plus W T star of v, right? Now from here I can again write it as W. I can take alpha inside, so it would be alpha T star u plus W T star v, right? But then again I can write this as W alpha T star of u plus T star of v. And this is true for all W, because W is any vector in V, so this is true for all vector W in V. Now, from here, what I can say that W T star alpha U plus V minus alpha T star U minus, or let's say plus T star of V is equal to 0 for all W in V. This is true. Now, can I say from here that this is equal to this?
Yes, sir.
Yes. So why this is true?
So we can take W equal to this second component.
Yeah, this vector, we can W, if we take W equal to this, then this implies that this inner product is 0. Inner product of this vector with itself is 0. But because of the inner product non positivity property, this is true if and only this vector itself is 0. But if this is 0, then that means this quantity is equal to this one. And so this implies that T star alpha u, sorry, plus V is equal to alpha T star U plus T star V, and this is true. So we started with any alpha and in F and UV in V. So this is true for all alpha in F and UV in V. So this implies that T star is a linear operator in V, and we are done. So T star is a linear operator on V, that satisfies this property, that means T star is an adjoint of T. Okay. Now you can see that where did we use the fact that V is finite dimensional. So where did we use the fact that V is finite dimensional?
Yes.
Yeah. So in the existence of this vector, right? So for any f's, so if V is infinite dimension, in that case also we can do similarly up to this step. But then we are not sure whether there exists this vector u such that we can write it in this way. And therefore the same proof will not work if we we change uh, V from finite dimension to infinite dimension. In fact, one can show that no other proof will work, or there exist linear operators on an infinite dimension uniprot space that do not have any adjoint, that do not have an adjoint. Okay, you need some extra condition for that on an infinite dimension uniprot. But for finite dimension, there is no issue, and we have a proof here. Okay, so now you can see that you have a if you have a linear operator on a finite dimension network space, then you can find its adjoint. That means T star. And you know that if V is a finite dimension finite dimension vector space and T is a linear operator on this, then there is a matrix representation of T. So there is a one-to-one map, or there is an isomorphism between the set of linear transformation on a finite dimension network space and on the set of matrices of appropriate size. The size depends on the dimension of V. So basically, we know that we know adjoint for a matrix. That means the complex conjugate transpose, and now we also have an adjoint for linear operators. So what I'm saying is that we have this set of linear transformation or linear operators, and we also have, if V is finite dimensional, then we have set of linear operators, and here we have set of matrices of size depending on the dimension of V. So if V is of dimension n, then we have this, and we know that there is a there is an isomorphism between these two. Now we have a concept of adjoint here. That means if I take any matrix A, then I can write it's A star. And we have a concept of adjoint here also. That means if I take any linear operator T, then I can write its T star. Now the next question is how these two things are related. And the obvious answer, or the obvious guess would be, okay, if I take this is my guess, but I'll see whether this is true or not. So if I have a operator T here, and if I write its matrix representation with respect to some basis, then my guess is that the matrix representation of T star is just the star of this. This is my guess. So in fact, we'll see that this is true if we choose an orthonormal basis. Okay. So this is what we are going to answer in the next. All right. So you can let me write this simple observation, which will be useful in proving what I just mentioned. So if we have a finite dimensional inner product space, let's say V, and if we have a linear operator on this, so this is just an observation, but I can write this. I'll write this as a result. So if we have a finite dimension inner product space and we have a linear operator on this vector space or this inner product space, since it's finite dimension, so we can fix a basis for this. So let's say this q1 to qn. This is an orthonormal basis because it's a inner product space. So we can talk about orthonormal basis. So suppose that this is an orthonormal basis of V. Then if we, so we, since V is finite dimension, T is a linear operator on this, so we can find its matrix representation. So let's say this is the matrix of T with respect to this basis B is equal to this matrix A, where the entries are denoted by Aij. Okay, so let these things are true. So let V be a finite dimensional vector space, and suppose that we have an operator on this V. Since the finite dimension, so let us fix an orthonormal basis. Since it's again it's an operator, T is an operator on finite dimensional vector space, we can find its matrix representation. So let us call this A. The entries of this matrix is denoted by Aij. Then, if this is the case, then you can actually write what are these entries, this Aij. These entries are explicitly, you can in advance you can tell what are these entries. So see, if I give you a linear operator on a vector space, on a finite dimensional vector space, you know that there exists you know what would be the, if I give you a basis, then you can say okay, one can find its matrix representation. So you will do some simplification, you will do some calculation, and you will find out. But in case of an inner product space, you can immediately tell what are these, what is this matrix. So you can tell that okay, the entries are this. So the you can easily tell explicitly that these are the entries. So this is what this result says, that in this case these entries are given by this inner product T of Qj with Qi. All right. So why this is true? This is very straightforward. Why this is true? So this is just one line proof. So you know what is this matrix? It's a how we write matrix representation. So if I take, so let's say for each j, what is T of Qj? So if I want to, if you look at this matrix here A, then what would be this TQJ? What it would be? So Q1 to Qn, they are the basis vectors, and we have a matrix representation. So that means I can write this T of Qj in terms of these matrix entries. So can you tell me what it would be? So it would be summation I equal to 1 to n Aij Qi, right? But then T of Qj, this is a vector in V. V is an finite dimensional inner product space. We have an orthonormal basis for this. So, and we know that, therefore, we know that this T of Qj we can also write. You remember, if we have a vector in V and if we have an orthonormal basis, then this vector V can be written as uh, this one, V of Qi, Qi, if you remember this. So here I will just apply this thing for T of Qj because this is also a vector in V. So what is this? This is just summation T of Qj Qi inner product where I is running from 1 to n. But if this is the case, then can I say that this implies that Aij is equal to T of Qj Qi for all ij? Is it true?
Yes, sir.
Why? Why this is true? From here, how can you say this? Just give me justification that this implies this thing.
They were linearly independent.
Yes, so you can take all everything to one side. So if I take this also to this side, then what it would be? This quantity minus this one for all I equal to 1 to n, for summation I equal to 1 to n. But then you know that this q1 to qn, they form a basis, so they are linearly independent, and therefore this implies that these coefficients are 0. That means aij equal to this. But this is true for all I and j. So therefore, if you have a you are in an inner product space and you have a basis for this, orthonormal basis for this, then you can immediately tell what would be the matrix entries here. Now, using this result, you can actually prove, which I will give you as an exercise, so you can work out this. So the exercise is following. So if we have a, let's say, finite dimension inner product space, and suppose that we have a linear operator on V, suppose that we have a basis for, we have an orthonormal basis, let's say Q1 to Qn. This is an orthonormal basis of V. Then you can show that the matrix of T star with respect to this basis V is the star of matrix of T. Okay, this is an exercise. So this is very easy. So let me give you some hints how to do this. So let us. So what we have to show, that this is true. We can find the matrix of T star because T star is a linear operator on V. T is a given operator on V. So we can find both these matrices. We just need to show that one matrix is the complex conjugate transpose of the other one. So if I just denote, let's say, so if I say, okay, let's say Aij, this denotes the matrix of T with respect to the basis B, and let's say Bij, this denotes the matrix of T star to this. So what should be my claim? My claim should be to show that Bij is actually Aij bar or Aji bar. It's a complex conjugate transpose, so it should be Aji bar, right? This is what is my claim now. But why this is true? This is true because of the above result here. This is one line proof. So okay, so let me tell you why this is true. So what we can say from above, that this Aij is equal. Yes.
तो यहाँ से सर हम ये कैसे पता कि ये कंजुगेट ट्रांसपोज है?
No, I'm not saying. I'm saying that claim. This is our claim to show. So I'm saying that this is, let's say Aij denote this and Bij denote the matrix of T star. Then our claim is to show that this is true. This is what we are trying to show. I'm not saying this implies. I'm saying that this is our claim. So I've written here. This we want to show. Okay. So this is this follows because of this this observation here. This is true for any operator T. So what would be this Aij here? Tell me what would be this Aij because of the previous result. It is just inner product of T of Qj with Qi. But similarly, you can write for Bij also, because Bij is a matrix representation of T star and T star is a linear operator. So from here, the same way we can say that this Bij would be T star Qj Qi, same way, right? But then this Bij I can write as, using the adjoint property, it would be Qj of Tqi, right? But then this is same as Tqi Qj bar. But then if you look at here, Tqi Qj, what it is? What is this one?
Aij bar.
Q star Qj.
Aji bar. So from here now you can see that matrix of T star is actually star of matrix of T. So this is very immediate. So basically this is not an exercise. I have already proved this. So this is, you can write this as a result now. Okay. All right. So let us do one example here. Suppose that we want to find, let's say, star of a linear operator. That means how to find adjoint of a linear operator. We have shown how to we have shown the existence of a finite dimensional network space, but let us see how to find it. So there are two ways. One is just use the definition, and the other one is this result. So if you are given a linear operator T on on a finite dimensional inner product space, then what you will do? You will fix a basis. You will fix a basis, any basis, orthonormal basis. Once you have a basis, orthonormal basis, you will find its matrix representation. Once you know the matrix representation of T with respect to this orthonormal basis, you will immediately know, because of this result, what would be the matrix representation of T star. T star you don't know in explicitly, but you know its matrix representation. Once you know matrix representation of a linear operator, then actually you can find what is the linear operator itself. So in fact, you know T star also. So because of this result, you can easily find adjoint of a linear operator. Okay, so for example, let us look at this example here. So consider this operator T from. So I have taken this simple example, but you can work out other examples from the textbook. So how it is defined? It sends uh, a triplet, real triplet x1, x2, x3 in R3 to this one, x2 plus 3x3, 2x1, 0. Okay. Now the question is find T star. Okay. So we have to find T star. Now, as I mentioned, there are two ways. The first way is you can use the above result. So how to do that? So let me do it in two ways, so you know both the ways. So the first method is that you just find matrix representation of T with respect to an orthonormal basis. So this is very important, that whatever we are doing here, this result is true only when we have an orthonormal basis here, because then only you can write the above result is true, which we are using in this proof. So first you have to find an orthonormal basis for R3. So when I'm saying that find T star, and I have not mentioned the inner product on R3, so you assume that it is the standard inner product. So R3, I have considered here R3 as a standard inner product space. We can say R3 with the standard inner product. So what we have to do here, we first fix a basis for R3. So tell me an orthonormal basis for R3 with respect to standard inner product.
Standard basis.
Yes, a standard basis. So you take this E1, E2, E3. So let's say this is a basis. So this is orthonormal basis of R3 with respect to the standard inner product. Then we can immediately find the matrix of T. Can you tell me what would be the matrix of T now with respect to this basis? Tell me matrix of T.
1 2 0.
1 2 0. But
Yes, sir.
here not 1 2 0.
0 2 0, sir.
Yeah, it's 0
Sorry,
2 0.
0 to 0.
Then
1
1 0
1 0 0.
next
3 0
3
0.
3 0 0 0.
Yeah. So you now have matrix of T with respect to this orthonormal basis. Now immediately once you know T matrix of T, you can easily write what would be matrix of T star with respect to this basis. So you know this also because of this result. It is just star of T. So basically, it is just you take the complex conjugate transpose, but here it is real. So complex conjugate transpose is just the transpose of this matrix. So it is 0, 1, 3, 2, 0, 0, and 0, 0, 0. All right. This is your matrix of T star. So you know matrix of T star also. So if this is true, then can you tell me what would be T star? You know the matrix of T star now. So you can easily write here what it is. So if you take any triplet here x1, x2, x3, then you send it to this one. Yeah, what it is?
2x2.
Yeah, it's
2x2.
2x. Yeah, 2x2. Then
then
comma
x1.
x1, comma 3x3.
3x,
1.
3x1. Okay, so now you can see that it's very easy to find T star, at least for such an example. The second method is that there is another way to find this. In some cases, this is also useful. The second method is just use the definition. So what we want, we want T star a linear operator, that means adjoint of T, that satisfies certain expression. That means this T of x, y is equal to x of T star y for all xy. This is what we want. Okay. So how to do that? So this is the way to find this is another way to find T star. So if I take two vectors, let's say x and y, so x would be of the form this in R3 and y would be of the form, let's say y1, y2, y3 in R3. So we don't know yet T star, but we know that if T star exists, then it will satisfy this thing that x1, x2, x3, T star y1, y2, y3. This is equal to T x1, x2, x3, y1, y2, y3. Right? We don't know at this point what is this T star we are trying to find, but if it exists, then it will satisfy this kind of thing. But what does it mean? This implies that we know T x1, x2, x3. So it is like x2 plus x2. So what is the definition of this at T? X2 plus 3x3. Then it is 2x1, 0. This is T x1, x2, x3. And then y1, y2, y3 you can write as it is. Now you write what is the inner product. What is the inner product? It's a standard inner product. So what it would be? It would be x2y1 plus 3x3y1 plus 2x1y2. This is what it would be. But the same quantity I can write as this also, this inner product also. It's x1, x2, x3, 2y1, oh sorry, 2y2, y1, 3y1. But then this is true. Now you can see that this, whatever I have written, this is true for all x1, x2, x3, uh, all vectors x and y in R3. But then from here, you can immediately say, because this is true for all xy in R3, so this implies that T star y1, y2, y3, if you define T star in this way, that this is equal to 2y2, y1, 3y1, then it is actually an adjoint of T. Okay, so you can see that it is the same thing as we have found using the matrix presentation. All right. So, okay, so let me move further. So what we have seen here, we have seen that, so what we can observe from here. So now we know a way to relate uh, adjoint of a matrix to adjoint of a linear operator. So we know some way here because of this result that if we choose an orthonormal basis, then matrix of T star is just the adjoint of matrix of T. So what I want to say is that basically there are two ways. So this is like a general information that there are two ways to study linear algebra. One, by studying, so you might have observed that while teaching you this course so far, I always try to relate results in the set of matrices and the set of linear transformation. Okay, wherever it was possible, I tried to connect that there is a way to go from here to there and so on. So basically there are two ways, two parallel ways you can say to study linear algebra. One by studying linear transformation, another one is by studying just matrices. So linear algebra means finite on finite dimension I'm talking about. So one you can do it by studying linear transformation, one you can do by studying just matrices, because we know that there is a way to go from one set to another set. So that means whatever study we do for, let's say, for set of linear transformation here, we can do similar study for a set of matrices here. If V and W are finite dimension, then it's possible because there is a way to go from here to there, right? So, but usually people prefer the second way. I mean, after a certain stage, people prefer the second way of learning linear algebra because it's more convenient. So the second method, which is studying by using matrices. So this method is more convenient. Why it is more convenient? Because it's easy to deal with matrices than, at least theoretically, it's easy to deal with the matrices uh, than comparative to linear transformation. So in fact, we can not only deal with matrices theoretically, but up to some extent we can also deal with them uh, in a nice way numerically also. So the second method is more convenient because we can easy to deal with matrices theoretically as well as numerically uh, than linear transformation. Therefore, in the rest of the course, my main focus would be on matrices now. Of course, I will, whenever needed, I will relate the results with linear transformation also, whenever needed. But I will try to focus on matrices so that it's easy to explain, it is easy to understand. But one can always derive results using by looking at the matrices. One can always write a similar result for linear transformation also, because we know that there is a way to go from here to here. Okay, so this is like a general comment. We will do it like when we define. I will in the next lectures also I will define things for matrices as well as for linear transformation. But in most of the cases, while explaining things, I will focus on matrices because it would be easy to understand. All right, so let me write the next observation then. Or let us prove this together. So this is an exercise. So if suppose we have a finite dimension inner product space, and suppose T is a linear operator this way. Okay, then you can say that if T is invertible, then T star is also invertible. Not only that, okay, so you guess the statement and then I'll prove. So look at this result here, the matrix representation here. So what I'm saying is that if suppose we have a finite dimension vector space and we have a linear operator on this, then if T is invertible, then can you say from here that T star is also invertible? At least you can guess. So if T is invertible, then what can you say about its matrix? And using that, can you say something about the matrix of T star? And using the matrix of T star, can you say something about T star? So this is something like this. So what can you say if T is invertible? Then what can you say about T star? Any guess from here?
Sir, also invertible.
It's also invertible. Why?
सर बिकॉज डिटर्मिनेंट नॉन जीरो है टी की मैट्रिक्स का
T की
then
matrix का. So yeah, so if T is invertible here, that means the matrix of T is invertible, which you characterize in many ways. So you are saying determinant of this is non zero. That means T star, this matrix of T is invertible. So this is fine.
then sir the determinant doesn't change after taking conjugate.
Hmm. That it changes, but if it is non-zero, it remains
Non-zero,
non-zero.
yes.
Yeah. So that means what?
So T star is invertible.
Yeah, that means the matrix of T star is invertible. But if the matrix of T star is invertible, this implies that T star itself is invertible. So this is, at least you can guess. We'll see that it is very easy to show also in a different way. This is, we are using some like a general argument, knowing that if T is invertible, then matrix of T is also invertible. Using this result, we have concluded whatever we have discussed so far. But I'll give you, I'll prove it using the definition, just the definition of adjoint. But at least you can say. Can you also tell me what would be the inverse of T star from this? What would be the inverse of T star?
The T
Since
inverse
you're,
beta star.
yeah, so you are saying that T inverse beta star, right? So from here you can at least guess what would be this. So if you take the, it depends again, using the matrices, you can say if you take the inverse of this, then it would be inverse of this, but that you can take inside. So it's a inverse of, it's a star of T inverse. Okay. So this is what is the statement, which you can easily at least verify using the matrices, but I'll give a different proof using the, just using the definition of this. So it also gives you a way to how to use this definition of adjoint. So then if T is invertible, then T, you can say T star is invertible. Not only that, and you can tell what would be the inverse. So the inverse of T star is just star of T inverse. This is what we have observed, and in fact it is true. So let us, so then again I will remove this as an exercise. I will prove this as a result. All right. So we have to prove that since T is a linear operator, we know that T star exists because V is finite dimension. So T star, we know that T star is there. So we know that T star exists. We just have to show that T star is also invertible. Now, in order to show that T star is invertible, I'll just show that T star. So we know that T is in this. This implies that T star exists and it is also a linear operator on this. Since V is finite dimension, I'll just show that T star is 1, 1 and I'm done. At least to say that T star is invertible, right? So let's try to see whether T star is invertible or not. So I will show that T star is invertible, or T star is 1, 1 by showing that null space of T star is just the zero space. Okay. So let us take any vector V in V and suppose that T star V is 0. Now I'll show that this implies that V is 0. Okay. Now what we can say from here, that this implies if t star v is 0, then this implies that for any vector u, t star of v, this inner product is 0 because t star v is 0, right? This is true for all u in v. Now can you tell me what would be the next step?
TU comma V.
Yeah, so it is tu comma v. This inner product would be 0 for all u in v, right? This is true for all u in v. Now can you tell me from here how to conclude that v is 0?
Then T of U equals to V.
No, so here u is free. So this is true. This expression is true for all u. So I should choose now. So this is true for all u, and I want to say v is 0. So I should choose this u in such a way that it gives me what I want. That means v is 0. So
is
what should I choose?
invertible. Use empty.
Yeah,
Therefore, there is some V, some W, so that W equals to
yeah. So you are saying, I understand what you are saying. So you are saying that you just take the pre-image of v as u, right?
yes.
So that means she's saying that you just take u as t inverse of v because t is invertible. So you can always find the pre-image of t, and this is 0 because this is true for all u. In particular, if you take u is this, then this is true. But then this implies that v is 0, but this implies v is 0. So therefore, this implies that t star is 1 1. But since v is finite dimensional, this implies that t star is also on 2, and that means t star is invertible. So this is fine. So if t is invertible, then easily one can say that t star is invertible. Now we have to find the inverse of t. We have to prove that inverse of t star is actually star of t inverse. So this is also not that difficult, but we just have to carefully write this. So next claim is to show, what is our next claim? So next claim is to show that inverse of t star is just star of t inverse. This is what is our claim. Okay. Now since t star is the adjoint and adjoint satisfy this property that t of u v is equal to u t star of v for all uv in v. This we know, right? So what I can do here, so what I'm trying to prove actually, I'm trying to prove, so if I want to show that inverse of t star is this one, then I should be able to show that that t star multiplied by uh, this t inverse star, this should be identity, right? If I want to say that this quantity here is an inverse of this, then I should be able to show that this is true. Because if I multiply t star with this, which is where I'm trying to show that inverse of t star, then it should satisfy this relation that this product should be equal to I, identity operator, by definition of invertible maps. So this is what I'm trying to show here. So I should take this thing. So I already have t star in this expression. I should somehow take this also into the picture so that I can further simplify it. So I should take inverse of t into the picture. So what I can do here, the right hand side here is equal to, you understand what I'm trying to do. So this is what I'm trying to do. So I'll remove this now. So in the right hand side, I can write as the same thing, but since t is invertible, using that, I will write it as t inverse t u t star v. Because is invertible, so t inverse t is just identity. So I can write this as this also. Right? Why this is true? Because not implies, I should write this equal. This is equal to this, right? But then what I can do from here? What I can say from here? Can I write this as T of U, T inverse star, T star V? Can I do that?
Yes, sir.
Yes, because I have already shown that T inverse exists. A T inverse is given to us. So T inverse is also a linear operator. Since T is a linear operator, so T inverse is also a linear operator. And it's on the finite dimension vector space, inner product space. So we can also talk about in adjoint of T inverse. So we have already proved, so there is no harm in that. So I'm taking now the adjoint of T inverse here. So this is what I have done here. But whatever I just wrote here, this is true for all vectors u and v. So that means what I can say that T of u, and then this I can write as I minus T inverse star T star v equal to 0 for all uv in v. Right? I just taken both the terms to one side, and then I have written this. Is it okay? But then this is true for all u and v. So what can we say from here? So in particular, if I fix my t, fix my u. So if I take u, what should I take u here so that I can say that this is equal to this? So this is, so what I'm trying to do here, that since this quantity, this expression is true for all u and v, I will take u, I will choose u in a particular way so that this quantity is 0. If this is 0 for all v, then I can say that I minus I is equal to this quantity. So that means I'm done. So this is what I'm trying to do. So what I should choose here? What should I take u as? So can you tell me what should I take u here?
T inverse.
T inverse.
T inverse I minus.
Yeah. So you are saying the in
Uh,
pre-image of this quantity, right?
yeah. Yes.
Yeah. So this is fine. So you just take u as pre-image of this the second component in the inner product. That means I minus T inverse star T star of v. Take this one. If you do this, then you can say that I minus T inverse star T star of v is 0, and this is true for all v. But then this implies that I is equal to T inverse star T star. So that means we are done, that the inverse of T star. So from here we can say that inverse of T star is this one, right? So we can say that this implies inverse of T star is actually star of T inverse, and we are done. Okay. All right. So let me define now a few type of matrices. We will talk about these matrices uh, like in a few lectures, but after defining eigenvalue eigenvectors. But since we know now at this point we know the adjoint of an operator and also adjoint of a matrix. So let's try to define a few more operators using the adjoint. So you know what is a Hermitian matrix? Do you know
Yes,
what
sir.
is Hermitian matrix? What is it?
Yes, sir.
What is it?
Conjugate transpose equal to itself.
The matrix itself, right?
Sure, yeah.
Have you also heard about unitary matrix?
Yes, sir.
What is it?
It's a with
Conjugate transpose
columns or
multiplied by
orthogonal.
matrix equal to
Identity.
Equal to
identity. Yeah.
identity.
Yes,
Right.
sir. A star equal to I.
Right. And how about normal matrices? Have you also heard about normal matrices?
Trans uh, transpose product into matrix equal to identity.
No, it's not identity. It's the unitary matrix.
Unit. Uh,
Sir,
So
A into A star equals
repeat
to A
A
star.
star equal to A star A.
Yes. So basically what I'm trying to say, so let me write this so that everybody knows. So let me write what you know. So you know, so I'll write this as a definition so that those who don't know, they also know this. So if we have a matrix, A of size n cross n over F, where F is either R or C. Then this matrix A is called, let's say first, self-adjoint or Hermitian, the same thing, two different names for the same thing. Self-adjoint or Hermitian if A star is equal to A. So where star is the complex conjugate transpose. It is called orthogonal. Matrix is called orthogonal if F is R, that means it's the field of real numbers. If this is true, and A star equal to A star equal to I, which is also equal to A star. So in the complex, in the real case, when F is R, this star is just transpose. So you can actually write it as transpose. Okay, A transpose is equal to this for the matrix. This matrix A is called unitary if A star A is equal to I, which is also equal to A star. So in the complex case, when the underlying field is the field of complex number, then this is called unitary. If the field is the field of real number, then it is called orthogonal. So why I define differently? Because in some books you will see that when they consider only real field, the field of real numbers, then they use the term orthogonal. And this matrix is called normal if A star A is equal to A star. Okay. Now this we know for matrices, or at least we can talk about this for matrices because we know the adjoint. But the question is, can we do similar? Can we at least define? We'll see what is the relation between in the set of this kind of matrices, and if we try to define this kind of operator also, we'll see what is the relation. But at least since we know star or we know the adjoint of an operator also, so can we talk about similar kind of? Can we define in the same way operators also, like a self-adjoint operator or unitary operator, normal operator, something like that? So we can at least do that because we know the adjoint. So the similar thing I'll define for matrices for operators also, but for that I need a finite dimensional inner product space. Then only I can talk about its star if T is a linear operator. So if T is a linear operator on these, then I know that star will exist. That means its adjoint will always exist. Then this operator T is called, or let me write, then T is called, say, self-adjoint or Hermitian. The same way we can define for operator also, Hermitian, if the adjoint of T is equal to the operator itself. It is called unitary if T star is equal to I, which is equal to T star T, and it is called normal if T star is equal to, or maybe since So T is called self-adjoint if this is true, it's called unitary if this is true, and it's called normal if T star equal to T star T. Okay, at least we can define. So this whatever I have defined, that makes sense, because we can talk about adjoint of T on a finite dimensional product space. But now the question is, what is the relation again? What is the relation between uh, an orthogonal, or let's say an Hermitian matrix and Hermitian operator? Or can we say like we did for matrix representation of T? We said that okay, if T is a linear operator, then and on a finite dimensional network space, and if we fix a basis, orthonormal basis for this, then the matrix of T star is just the star of T, the star of matrix of T. This is what we have seen. So can we also say something here also, like if T is self-adjoint, then what is the relation between matrix of T and matrix of T star, something like that. So what I'm saying is the following, that can we say, so can we say that if T is adjoint, or T is self-adjoint, or T is Hermitian, then the matrix of T is same as matrix of T star? Can we say this with respect to some basis? Or when T is unitary, then matrix of T and T star satisfy this relation. Similarly for unitary matrix also. And the answer is yes, you can do that. I mean, one can prove that the matrix representation of this kind of operators also satisfy similar kind of relation. So let me write this result here. So what you can do here is the following, that sorry. So let me write this as a result here. So suppose that we have a finite dimensional inner product space, and suppose T is a linear operator only. Then you can say that T is, so what I'm saying is that whatever I'm doing or whatever I'm writing next, this gives you a way to check whether a given operator is Hermitian or unitary or normal by looking at their matrices, looking at their matrix representation. So this result says that if we have a finite dimensional inner product space and T is a linear operator on this, then this operator T is Hermitian if and only if. So this is an if and only if result. So this is true if and only if T is Hermitian if and only if the matrix of T with respect to, or matrix of T is equal to matrix of T star with, for every orthonormal basis. This is important here. For every orthonormal basis, if this is true, then it's Hermitian, and the other side is also true. Similarly, you can say that this T is unitary if and only if T star T, this is equal to identity, which is also equal to this one, and this is true for, again, for every orthonormal basis. If this is true for all for every orthonormal basis, then you can say that T is unitary, and vice versa. Similarly, you can say that it is normal if and only if this is true. And again, this is true for every orthonormal basis of V. Okay, this is proving this is not difficult. So how much time we left? So we have 15 minutes. I'll prove this for one case. So let's say for unitary case I will prove, and then using similar idea you can prove for other cases also. This is again not that difficult to show. So let me give you quick idea for how to prove the unitary case, and for the other two cases you can prove yourself. Okay, or you want to try yourself. So I can leave this as an exercise. So I'll leave this as an exercise. So you try it yourself. Okay, just work out this thing. You can easily find this in any textbook, but you try to do it yourself, and then if you don't get it, then I can help you in that. So that's all on this inner product space. So with this we like sort of conclude at this point the inner product space. Later on we can come back to these matrices and we can solve problems, and we can talk about more about these matrices once we introduce inner eigenvalue eigenvectors. So why I introduce these matrices? Because explaining eigenvalue eigenvectors would be easy for me if you use this type of matrices also. And in some cases it would also be easy to give you examples when we have like some kind of class of matrices. So now you have this. So in the next lecture would be on Tuesday, where I will talk about applications. Before starting the eigenvalue eigenvectors, I will talk about uh, application of eigenvalue eigenvectors in more general, and then we will introduce the concept. Okay, so again on Monday we have a quiz. It is at not Monday, so I think you suggested Tuesday. So on Tuesday at 3 p.m. we'll have a quiz. I'll send you the details regarding the quiz. So it is whatever we have covered after minor exam. So basically this inner product. So I'll give two questions. The questions would be like easy if you know the like if you know the results and if you know the basic idea. So I'll give you two questions for 25 to 30 minutes, and you try to use whatever we have discussed in the class, and try to use the definition and try to use the results which we have discussed in this inner product space to solve these problems. Okay, so if you try to like look for these problems on Google, then you won't find. But if you just use the basic idea, the basic results we have defined in the class, or we have discussed in the class, then you would be easily able to solve these problems. Okay, so and there was also one more suggestion from your side that can we have one extra quiz so that we can consider like can we have one extra quiz so that best of 3 out of 4 can be considered. So this we will see depending on how much time we left. I mean, when we'll conduct the third quiz. It's depending on that we will see whether, or and I will see your class average. Based on that, we will conduct the fourth quiz. But right now, I mean, as we had announced earlier at the beginning of this course, there would be 3 quiz. But depending on when we'll have our third quiz, we can have one more. Okay, but at this point, I won't commit anything. But the next quiz would be on Tuesday. Okay, if you have anything, you can tell me. Otherwise, we stop here.
Sir, Tuesday is holiday.
Tuesday is what?
Holiday, sir.
So for what is Tuesday? I mean, for what this is a holiday?
Semester break.
It's a semester break. Okay,
Yes.
but you only suggested me this See, I asked you for Thursday, that means today, or Friday. Then you said, some of you said Friday, but then you cancelled. Then Saturday, then again you cancelled. Now you suggested me Monday. Monday again you cancelled, and then you suggested me Tuesday, and Tuesday also now you are saying. Anyway,
No,
this is an online quiz. So even if it is a holiday, you should be able to attend. It's not like you have to physically appear. Okay, it's
no, sir.
just for half an hour.
But you are saying that class.
So if class is not there, then that is fine. But the quiz would be there.
Yes, sir. Okay.
Okay. So if the I'll see the calendar, academic calendar. If the class is not there, then we can't do anything. I mean, but if the quiz is scheduled, then it would be scheduled on that time. So right now itself, you tell me whether you want it on Tuesday or not. Because if you don't want, then we'll prepone or we will postpone. We'll see what are the other like possible timing. But if it is scheduled, then it is scheduled at that time. It won't be changed. So that's why I'm taking your suggestion. Tell me something. If you like, you're saying that Tuesday 3 p.m. is fine. Then I would say that go for it, because it won't disturb. It's a holiday. It will take only half an hour, and it won't disturb your other lectures also in the coming days. So just finish it. Finish the second quiz so that we'll have at least enough time for the third quiz. And if we have some more time, then we can have one extra quiz. So it's your loss only if you are delaying this quiz, because then we'll have only 3 quiz. And I'm planning, as you have requested, if the time permits, we can have 4 instead of 3. Okay. So
Okay, sir.
Yes.
can we have it on Tuesday at 3 p.m.?
Yes.
Yes, sir.
Yes.
Okay. So I'll send an email regarding the syllabus. As I mentioned already, that it is just inner product, whatever we have covered after till today's lecture, after minor exam, that would be there in the quiz. It would be very easy. Easy in the sense, easy like quiz 1, but you will have to think and you will have to write. So just look at your notes, try to think how these results can be used, whatever we have discussed, and then you will be easy to answer this question. You would be easily able to answer. Okay, so we can stop here and have a good day.